nanohub.org.
Online simulation and more for nanotechnology.
Welcome back to ECE 695, Fiber Optic Communications. This is the second week in the fourth lecture. Today I'll be covering the topic of lasers. Many people probably already know a little bit about lasers, but we'll go into more details. And basically I'll be talking about three primary subtopics. First, the kind of the general principles of lasers, and then some specific examples of transitions in lasers, and then how that can help us write down some generic rate equations, which will then set us up for like kind of the later discussion about both modulation and other factors that play into optical communications. Okay, so first of all, like what are the essential components of a laser? So we can of course refer back to like what the the word laser stands for. It's light amplification by stimulated emission of radiation. And this was actually inspired by the maser, or the microwave version of a laser. And it was found that in the case of maser and then also laser, you need like basically the same three fundamental elements, which are closely connected to one another. So first is gain medium. Okay, so the reason why gain medium is so important is because of what we talked about last week, which is that stimulated emission and absorption are basically inverse of one another. So if you have light coming into a system, then if you have a very low level of excited states, then you're much more likely to absorb the light and thus excite those electronic states. But if you already have a lot of excited states, then it's more likely that the opposite will happen, and you'll basically have stimulated emission, which is shown here very schematically. Single photon comes in, and then two photons come out, both the original photon plus a clone of the original photon. So that's the stimulated emission process. And the gain medium is necessary for that to happen. Otherwise, it would be absorbing the light instead, doing the opposite of what we want. Then the second thing that's really important is optical feedback. And the reason we need that is because if we have a photon that we want to keep cloning, then we have to keep it in the cavity long enough so it can be cloned enough times and basically grow in intensity. And then the third thing is basically pumping. And the reason why we need pumping is that as we have stimulated emission happening, then our gain medium may transition to an absorption medium unless we keep pumping that original medium in some way or another. And of course, there are a wide range of ways to do the pumping. So without going into all the details right now, we could say basically there's an optical pumping scheme, or basically there's a separate optical input that's basically pushing us into the excited state and thus maintaining that population version. Or there could be electrical pumping. And so like if you have a handheld laser, typically that's electrically pumped, like a helium neon laser, and I think I'll talk about that in a little more detail later, which is a red laser, basically uses electrical discharge and gas. But the other thing that you can have is current injection in a semiconductor, and so oftentimes green lasers are coming from current injection. Another option is chemical reaction, and so of course some chemistry will allow us to excite molecules into like higher energy states. Of course, the drawback there potentially is once you run out of reactant, then you can't run the laser anymore, so you need a lot of fuel. And then there's even strategies that involve using charged particles and their kinetic energy. Okay, so there are a lot of different ways to do this pumping. Okay, so basically the way that we can look at it is we need to be able to augment the input signal using this external power source. And the pump has to be strong enough so that even when the laser is operating, it provides population inversion. Okay, so that's really the key takeaway. So if we look at what is population inversion, I mean, just very simply, if we define that there's a two-level system, and this may be simplification of reality. then we could say that the lower level has population of N1, and then the upper level N2. So that's a higher energy state. And so then if N2 is greater than N1, so that means our capital N parameter is positive, then we have more excited electrons or states in the system than ground state. And so that means that you can act as amplifier. And then conversely, if N is negative, then that means that it's an attenuator. So then it will absorb light. Okay, so then basically you get something like this, where input light comes in and then it's attenuated according to Beer's law. So you don't really want that in a laser, you want the opposite. So now if we write down like quantitatively what's happening here, so if we say that there's like a photon flux that's coming in, okay, so we have a photon flux phi, then we can actually say that there's a gain in the photon flux of d phi. So then we basically have phi plus d phi as we go through a gain medium, okay? And so then the rate at which this gain happens typically depends on the distance that we're traveling. And so we can actually say it's basically a pumping rate, which depends on the inversion factor n, so that's the first parameter, times this w sub I that we defined last time, which is a kind of a transition rate in the system, times the thickness. And so we basically get this n wi times dz gives us this phi plus d phi. And so once we write down the equation like this, then we can actually expand this by expanding on w sub I. So in other words, we now have like basically d phi is equal to this dz, and wi dz, divide both sides by dz. Okay, so that gives us an nw sub I for d phi dz. And so this expression w sub I also depends on our phi times this factor of lambda squared divided by 8 pi times the spontaneous emission lifetime. And so remember last time we said that the Wi, or absorption, and simulated emission rate goes inversely with the spontaneous emission lifetime times this Lineshape function g of nu times our phi of z. Okay, so those are basically the expressions. And then if we write this expression more simply, then we can write it as basically gamma times phi. Okay, so now that means that there's basically going to be exponential gain in phi as we travel through the medium. And so this is kind of like the opposite of what happens with Beer's law. So of course, you know, with Beer's law, typically light comes in and then it attenuates as function of z. So this I of naught, I naught, and then I of z. But now we're saying actually now it's the opposite. So we start off with maybe a low intensity and then it goes up exponentially. So this is Beer's law. And then this is essentially a gain medium where we have I of z is now growing because we say phi is proportional to I. Okay, so now our gain medium gives us this kind of behavior, right? So in some sense, it's very simple, but it shows you that the behavior is completely opposite, and it's all driven by this n. And so why is that n so important? So if n was negative, which is what we normally think of in Beer's law, then we would actually reproduce this kind of absorption behavior, because now the gamma factor would be negative, right? And so then it would be like e to the minus alpha z or something, right? So that's what we normally see in other media. So then basically now we have a definition for the gain coefficient. And this gain coefficient depends on the population inversion n times this lambda squared over 8 pi t spontaneous times this Lineshape function g of nu. Okay, so basically, if we're in thermal equilibrium, then of course, in general, if there's like a large gap between these two states, then we expect that the number of ground states is going to be much greater than the number of excited states, right? So if we're not pumping it, then we expect that this will almost certainly be a loss medium. Even if we have a small gap, we'll still have N1 greater than N2 in thermal equilibrium. So that means that basically we'll have a net loss of photons. So it's only by pumping it and pushing it out of thermal equilibrium we can really get to population inversion and thus a gain medium. And so basically the way that I've written it here, the definition of gamma is like minus alpha, where alpha is basically the absorption coefficient in a standard loss medium. Okay, so these are all closely related, these concepts. But you can see the sign is very, very critical. And of course, this expression here is just telling you like what is the population ratio between the excited and ground states in thermal equilibrium. And so by definition, E2 minus E1 is positive. So that means that you always have N2 over N1 is less than 1 whenever you have a positive temperature. Now, so what does that imply about the temperature of a medium where N2 over N1 is greater than 1? So if the N2 over N1 ratio is positive, like greater than 1, then what does that imply about the temperature of the system based on that expression? So I think the way to look at it is maybe to, first of all, find the eraser. Hold on. So if we take this ratio, okay, so let me just write that on the board again. So we have N2 over N1 is equal to e to the minus, and it's written as E2 minus E1, but let's just call it the band gap, just to be simpler. So minus EG over KT. Okay, so now we're saying normally EG is positive, T is positive, and then we plug this in, we get something less than 1. Right? So then maybe N2 over N1 is like 0.1, maybe it's like 10 to the minus 10, some number less than 1. So if N2 over N1 is greater than 1, then basically what we're saying is we must have this whole argument is positive, right? Because you basically, to get an exponential that results in a number greater than 1, you must have positive exponent, right? So that means that we have minus EG over KT is positive, right? So if EG is positive, then how can we satisfy that condition? Right, exactly. So one way to look at these systems for lasers is that actually they have a negative temperature, right? And so this is like kind of a weird concept, I admit. Like why would a system have negative temperature? So the point is it's not in equilibrium with its environment, but we basically have pushed it into the special state where it's out of equilibrium with its environment, and that allows it to act like in the opposite way that normal material would act. And so that's just like one way to like kind of think about this system and its difference from normal states of matter. So thank you for answering. So basically, once we have this gain coefficient established, this gamma, then we can also define like the total gain. And so the total gain is defined as a function of frequency typically. And so the way that we look at it is, since we have this exponential growth from 0 to d, basically the length of our gain medium, then we basically have an intensity I sub naught here, and then we have an intensity I sub naught times e to the gamma of nu times d. Okay, so that's basically like our total intensity at the end. And then we can also say that the gain is basically defined as the ratio of the output divided by the input, which is e to the gamma of nu times d. Maybe I should write it as I0 nu, okay, divided by I0 nu. And so then these two terms cancel, and so then that leaves us with a gain of e to the gamma nu of times d, right? So then that's basically the expression I have there. So that's telling us basically like what amount of amplification is possible in this laser. And of course, this is like a somewhat simple expression, right? It doesn't account for multiple passes in the loop, of course, and it doesn't account for basically the interaction between the stimulated emission and depletion of the gain medium and so on, right? So this is not a complete expression, but it gives you some idea. Any questions before we move on? Oh, so basically this is like I0. So this is basically the intensity when you enter the gain medium. And then I just added the nu to say like basically there could be different intensities at different frequencies. And so the more general expression is actually I0 nu here, and then I0 nu here. And so then this basically saying like there's like some spectrum that enters the system, and then the spectrum that leaves the system is amplified by this gain factor. So another way to put it is basically the output at D as a function of nu is equal to the gain factor G of nu times I0 nu, if that makes sense. Okay. Any other questions then? Okay, well, thank you. So then the next part, I'll talk about the transitions that can happen in laser. So this relates back to this lowercase g of nu, which is called the Lineshape function. And so basically, when I wrote down this g of nu, I didn't really go through that in detail, but basically the definition of g of nu is the following. So if you look at this picture here, what this is showing you is that there's a function that's defined, typically looks like a Lorentzian, where basically it has an integrated area of 1, and then it has a peak, like right at this frequency we call nu naught, which is typically like thought of as a resonant frequency, and then it has a line width of delta nu. Okay, and this delta nu is the full width at half max. So basically at half of the maximum value of g of nu, we have like a range of plus or minus delta nu over 2. Okay. And so then that results in this equation you see here for the line width, which is basically gamma at nu naught, which is right in the middle, times this Lorentzian, which is defined in this way. So this Lorentzian basically reproduces the shape that you see below, right? So that's where this is coming from. And so this is normalized so that g of nu is always equal to an integrated area of 1, but then you can actually then convert that g of nu into a cross-section sigma of nu by multiplying by some factor s. And s is basically the area under the cross-section across all frequencies. And so S is defined as integral of sigma of nu d nu from 0 to infinity, right? So that's basically the expression you see down here. And so I realized that there's a lot of terminology all at once, but the key takeaway here is just that most laser resonances, especially like atomic resonances, typically have like this Lorentzian type shape. However, this is not the only type of shape that's possible. So I don't want to say this only way to look at it or to understand all transitions, but it's a nice place to start. So particularly if we're talking about atoms, then this is a good model. And so I briefly alluded a few minutes ago to the helium neon laser. And so that's basically a famous red pointer laser, and that's electrically pumped. And so that is pumped by gas discharge. Typically the way that it works is that you have a helium cavity, and then it's pumped by electrical discharge up to these excited states, which are called the 1s, 2s1 singlet and triplet states. Okay, so that's basically the difference between these two states, singlet and triplet. That tells you something about like the spin alignment, basically if they're parallel or anti-parallel. And then what's interesting about this system is when helium is in proximity to neon, helium can collide with neon and then basically fully transfer its energy into the neon energy states that are just below the helium state. So it's almost inelastic, or yeah, it's mostly elastic collision. Basically, helium transfers most of its energy to neon. Basically, these two states that are shown here, but you're particularly interested in the transition from the so-called singlet state in helium to this 5s excitation in neon. And the reason why is because basically once this neon is pumped, then it can basically have two transitions into either 3.39 microns for infrared or 633 nanometers for red lasers. Okay, and so basically these two transitions are very critical to determine behavior of the system. And then that brings up another question of just like, why is it all happening in these directions? Like, why doesn't it happen like in other pathways, right? So the other pathways are called forbidden transitions. And don't take forbidden like too literally. Like forbidden doesn't mean that it's absolutely impossible, but it does mean that it's like strongly suppressed. And so in particular, you're very unlikely to go, say, in neon from here to here or here to here. And the reason is because they both have odd parity. So that means that you can't just emit a single photon to get that transition. You need to have like multi-body interaction for that to happen. But you can go from an odd parity state to even parity state more easily. And so that transition is much more favorable. So that's why you typically would get one of those two transitions. So then, of course, which one would you get? It actually depends on your cavity, right? So if you have a cavity specifically tuned to 633 nanometers, then you'll get lots of red light. Otherwise, you might get more 3.39 micron infrared light. Okay. So basically in, all these systems really, it's all about basically what transitions exist in individual atoms, and then how do those atomic states interact with one another. This is just another example of like a carbon 5+ transition, like at 18.2 nanometers. So this is like extreme ultraviolet transition. You can see that obviously it's a much shorter wavelength than the other example that I showed you. But in both cases, whether you're talking about like a very low energy transition or something that's like, on the order of like dozens of electron volts, the principles are very similar. If we look at a solid now, then it's going to be a little different from the atomic base lasers. Like, because both of the lasers I just showed you, whether it's like the helium neon or the C5+ extreme UV, like those are both gas phases, and thus they're characterized by atomic transitions, which are very sharp. In solids, typically you're forming a crystal lattice, and then you have bands of states. And these bands of states actually have a range of energies, so the transitions may not be as tight. And so this is just showing an example from a solid, which is rhodamine 6G. This is a well-known laser dye. And so you can see this basically a small molecule, and this molecule has states that are depicted here. And you can see basically there are a set of singlet states and a set of triplet states in the system. As it turns out, like the favored laser transition is actually singlet to singlet state. You can also see that there are triplet states that can interfere with that process. If you excite triplet states by accident or just unavoidably you excite some of them, they may not benefit your laser transition, so that reduces efficiency. And then second, even within the singlet to singlet transition, there's a range of energies. So that means that your emission wavelength range or gain wavelength range can be much wider than the atomic transition. But you can still potentially narrow it down by using optical design to favor certain transitions. So it's not that all is lost in the solid. So of course, like, this goes back to the definition of energy bands. Now, most of you know this, so I don't want to belabor this too much, but just to compare the atoms to materials, then you know that in general, you can think of metals oftentimes as having like a range of energies, especially like near a band gap. So then basically there's not much of a band gap in the metal, but then as you go to semiconductors and insulators, essentially the band gap becomes larger. And so that means that there are going to be kind of quasi two-level systems in semiconductor type materials as well as insulator type materials at different energies. Just to give you some examples now, you can actually look at these interesting, first of all, on the left, it's kind of like a quasi-atomic system almost, in which you have individual atoms, which are either rare earths or other dopants like chromium, that actually have like a relatively narrow transition. So you can see here, for example, there's relatively narrow transition associated with this chromium 3+ ion. So you basically excite it in alumina, possibly through electrical or optical doping, or excitation, sorry. And then this actually couples to this very narrow transition here. And then you can see similar things can happen in neodymium. So neodymium has like a well-known 1.064 micron transition. And so that transition actually is kind of a cornerstone for creating a neodymium YAG laser. So that's something that's used for green laser pointers after frequency doubling. But if you look at the neodymium glass, what's kind of surprising is that the transition is actually a slightly different wavelength. So then the reason why is basically the dielectric environment slightly influences the energy of the transition between two otherwise identical states. And then if we look on the right, then you can actually see that the transition happens a little differently, where basically, like, rather than having like really discrete states that are associated with these rare earth transitions, we instead have oftentimes, like for things like gallium arsenide, we have a range of conduction band energies and valence band energies, but we oftentimes have the laser transition happening near the band edge of the semiconductor, and this acts like kind of a quasi two-level system. However, the efficiency is not necessarily that great if you just do this in bulk, as I'll explore further. So there's actually a number of strategies where you basically try to tightly confine the states and actually eliminate some of these extra states that can reduce the efficiency, such as quantum wells and, of course, quantum wires, quantum dots. And so all these quantum designs, right, so without going into too much detail, can give you like much sharper transitions than you would otherwise get. And so sometimes these are called artificial atoms even. And just an example of that is up here. And so this is a picture from a lab at Arizona State that's basically showing you that if you take these semiconductors and then you make them into quantum dots with well-specified radii, then they can actually have very strong transitions at targeted colors. And so you can basically, in principle, do almost any color in the rainbow very easily. And of course, this is actually a really interesting direction if you need an alternative to rare earths for sharp laser transitions. And of course, in principle, this can be also much more efficient than having like a bunch of transitions like you have in a gallium arsenide laser. So any questions? All clear so far. Okay, good. So I have about 15 minutes. So now I'm going to try to introduce the general rate equations today. And then after I introduce the general rate equations, then we're going to try to use those to describe particularly like 3-level and 4-level laser systems. And then that will hopefully lead us back to understanding how do we use these kind of lasers for optical communications. Okay, so basically the rate equations are critical because they're going to tell us, first of all, like what transitions are relevant in lasing. Okay, so that's number one. And then number two is it'll tell us how much power we get out of the system and also how efficient the system is. in the presence of other processes, because there are many processes happening in these laser systems at the same time. So we have to look at all of them at once and capture at least like the most critical transitions and changes in population simultaneously. Okay, so basically the way that we'll try to construct the rate equations, we'll start with the laser transition. And so here it's basically written as 2 and 1, where basically N2 is associated with the population in this state 2, and then N1 is associated with the population in state 1. And we're assuming that N2 minus N1 is supposed to be positive if we're lasing. Okay, so that's a population inversion. So these 1 and 2 states are basically the population inversion states. So of course there can be many other states in the system. I just showed you a whole bunch of examples that were more realistic, but this is like kind of the foundation for doing all the math. What else is happening here? So basically you can see there's basically a spontaneous emission process, so basically going from 2 to 1. And we said that that's inherent to all these systems, so they always have spontaneous emission. So we must account for that. You can't avoid that. But then there's also potentially non-radiative transitions. And so we don't always have non-radiative transitions, but we may. And we should account for those in case they are happening. And then we even have like this tau2 process where basically we go from excited state to some other state that we don't necessarily want. So we need to be aware that this can happen. And then another thing that's very critical is that the 1 state can decay. So why is it so important that the 1 state can decay? Does anybody know why? In a laser? Yeah, why is it helpful for it to decay, I guess, in a laser? Right, exactly. So the point is, if we don't have any decay of the 1 state, then it's almost impossible to maintain population inversion. So we must have 1 being basically pulled out, and then we have to be able to pump it back to state 2, right? So we first pull energy out of the ground state, quote unquote ground state in the laser transition, and then push it back to excited state. So you have to kind of do both and maintain that cycle. Yes. Yes, exactly. So if you go back to some of the examples that we had earlier, just to kind of illustrate this a little more, you can see that actually the foremost excited state is actually the singlet of helium, which is in the upper left up here, right? And so this is like something we're trying to get to. But then if we look at it in terms of the terminology we just defined, then this is basically our state 2 here, and then this is our state 1 here. You can see that this is not the highest excited state, and this is also not the lowest ground state, but it's actually, these are both intermediate states. And then there's like a full ground state that's all the way down here. It's actually off the chart. Right. It's easier for which one? Sorry. Well, so I think the point is both are possible, but it also depends on the environment that they're in, right? So if you're in an environment where 633 nanometers is selectively enhanced by mirrors, like you've basically designed it so that you have feedback, then you're going to preferentially emit 633 because the stimulated emission is pushing you in that direction because of the presence of 633 nanometer photons already. So if you have something that basically damps out the 3.39 micron, you won't have like lasing at that wavelength. But if you design it the other way, you wanted to encourage 3.39 microns, then you can do that. But one of the key points here is that these two transition wavelengths are like well separated from one another. So usually you can design a laser to have one or the other. So usually you don't want both in general. Usually you either care about creating visible light like laser pointer, or you're doing some sort of infrared spectroscopy or something, so you need the 3.39 microns. So you kind of decide when you design the laser which one you want to encourage. Sure. Yeah, sure. Yeah. Well, the transition's happening in the neon. So I think the way to look at it is helium is there to help us with the pumping, because it's possible. Helium has much simpler set of states. So you can reliably get to this fairly high energy excited state in helium through voltage discharge into the gas. But then you need it to basically collide with the neon atom so that neon atom gets to this 2p5 5s state, and then basically has the laser transition. So that's basically what's happening. And then of course it loses the rest of its energy subsequently, typically through non-radiative collisions until it basically resets and then allows you to keep pumping the helium and neon. Sure. Okay, so then going to the rate equations real quick. So basically the simplest way to look at this system is the following. So if we say that there's an isolated two-level system, and of course this is a simplification, then the rate at which the upper level energy or population changes will be dependent on three factors. Okay, the first factor will be basically the spontaneous emission decay. Okay, so that's this minus N2 over T spontaneous. The next term will actually be excitation from absorption of photons. Okay, so this is N bar. So that's the average number of photons interacting with it times N1 over T spontaneous. So that's the absorption term. And then finally, we have basically the stimulated emission term, which is minus N bar N2 over T spontaneous. And so then this actually shows you why you need to have, like in very concrete terms, why you need N2 greater than N1. Because otherwise, like you'll have basically, as N bar becomes positive, then you'll actually otherwise have like excitation of this two-level system beyond what you want from the input light. But that's the opposite of what you're looking for. So that's an absorption process if N1 is greater than N2. But on the other hand, if it's N1 less than N2 on net, then you have simulated emission. So that's basically what this is showing, just in the simplified case. And so if we just write this down in a slightly different terminology in terms of this delta n, then we can write down now a delta n differential equation. So that's just derived from the equation for N2, assuming N2 plus N1 is equal to some fixed total. Now we have basically that the rate of change of the delta n depends on the spontaneous emission lifetime plus the population of photons. So basically these two terms add together minus this so-called NT, where NT is basically the total, right, divided by T spontaneous. So that last term will always be negative, but then the first term should also be negative when we write it in this framework. And so that gives us like a very simple solution. So if we just solve the differential equation, I won't go through the math, but you know how to solve first order differential equations. So you basically get like an exponential where basically it's a constant times this e to the minus 1 plus 2n over tau spontaneous times the time that's elapsed minus a constant. Okay, and so if we look at like what that means in the absence of pumping, that just means that you'll have exponential decay of the excited state, right? And so that's because like you have absorption process happening. So just to show you concretely what happens, if the light is off in the system, then you see basically the amount of ground state energy basically goes to 1 over time, right? Which is expected. So that's basically just reverting to thermal equilibrium. However, if you turn the light on, then of course you go from thermal equilibrium state, where basically almost all the population is in the ground state, to something where you have much less energy in the ground state, right? And you have much more in the excited state. So then basically your delta N is going from -1 to something that's close to 0. However, the key thing here is that it's not going exactly to 0 or a positive value. So that's telling you that even if you're putting a bunch of optical light into the system at the transition wavelength, you can't really push it into population inversion. And of course, you can like turn the light on and off and hope that it'll go into inversion, but it's just never going to go into inversion. And that's basically determined just by the structure of these equations, that it can't go into inversion just from direct pumping of an isolated 2-level system. So that tells us like 2-level system by itself without any external interaction will never become a laser. So you have to add something else, basically. That's kind of the bottom line here. So we need a process that will both increase the number of atoms in 2 while also decreasing the number in 1, which Heimbody correctly pointed out. So we need to look at both 3-level and 4-level systems that can help us achieve that. So just as an example, basically, we have a very simple concept here where we just have some pumping rate called R2. Okay, and so now R2 is basically just adding a positive term into our dN2 dt differential equation. And otherwise, like, it could be very similar as before. And then the second thing we have is a minus R1. And basically, R1 is basically pulling energy or population out of this lower state. Okay, and this could be, non-radiative process. It could be radiative, like both are possibilities at this point for both R1 and R2. So the key thing here is that now we have this positive R2 and we have this R1, which is defined with a minus sign. So it's basically negative for 1. And so we're basically doing both things at the same time, like pumping 2 and de-exciting 1. And so this is actually going to allow us to break the constraint that we had earlier where we couldn't reach population inversion. And so we can actually now get a population difference that can potentially give us N2 greater than N1, which hopefully makes sense. And then this is just the mathematical result of this particular set of assumptions about R1 and R2. And so this tells us that if you look at this expression, like the form of this, then you can see that basically positive R2, as we defined it, will increase like the net population inversion that's possible in steady state, as well as like a positive value of R1. Now, of course, with that said, that does put certain constraints on the ratio between tau1, like basically the spontaneous decay of like this ground state and transition, divided by the spontaneous transition between 2 and 1. And so you need actually, in general, if you want N naught to be positive, you need tau1 to be less than this spontaneous transition between 2 and 1. So basically, the ideal case, we have like a relatively large tau2 or tau2-1. And we also have like a relatively short tau1 if R1 is less than R2. Okay. But in general, R1 and R2 being large is the most important thing. And this basically just showing that typically we can assume that the tau2-1 is close to the spontaneous emission lifetime. So that can help us understand like conceptually what's happening. And of course, tau1 should be less than the spontaneous emission lifetime in order for this population inversion to be large. So then basically, like just to expand on those previous equations, like basically it was slightly simplified because we didn't include all the transitions that can take place. We basically just included the first two terms, but we also need to include both stimulated emission and then absorption. Okay, so if we add stimulated emission and absorption to both, then you see they enter both of these differential equations for the upper and lower state, but they have opposite signs. So basically takes away from, like the stimulated emission takes away from population of N2, adds to N1. And then of course, absorption of incoming photons adds to the population of N2, subtracts from N1. So you can see in both cases, like basically we're adding terms that are dependent on this population difference, like N2 minus N1. And so in order for population inversion to be maintained, then we have to have a pumping rate that overcomes the drain that's associated with operating the laser system, right? And so hopefully that makes sense conceptually, that to maintain the steady state, we can't basically be pulling more energy out through stimulated emission than we're adding back into the system through pumping, while including like the parasitic losses in the system. And so the way we can illustrate that general framework is that we have this pumping rate R2. It's going into this upper level system of 2. And then we basically have this spontaneous lifetime, okay? And then that's causing some decay. And then we have stimulated emission as well, causing additional decay. And then we have some absorption, and that absorption partially offsets the stimulated emission. But the net effect is basically some stimulated emission is happening. And then that stimulated emission needs to not be happening faster than R2. Like ideally, R2 is equal to the stimulated emission plus spontaneous emission plus any other loss mechanisms. So then you can maintain like a steady state population inversion between these two systems. And so then if we solve this in the steady state, then we basically can now get the total population inversion is going to be this N naught that we calculated earlier, divided by a factor that's 1 plus tau spontaneous times this transition rate, which again is close to inverse of the spontaneous emission lifetime. And so you can see this tau s is basically, going back to the previous picture, dependent on tau 2. So this basically the total rate of loss of the upper level state 2 plus some additional contribution from tau 1, the loss of the lower level state, times a correction factor. So I think that pretty much gives you an idea. This is just showing what the steady state population difference looks like as a function of W sub I. So of course, when Wi equals 0, then we get the previous result that we calculated earlier, but then it basically starts dropping pretty substantially as we go to larger values.